So let's, moving away just a little bit from the listed problems, let's consider our 0.6 liters of gas at 130 kilopascals, but this time we're going to allow it to expand quickly to 100 kilopascals, expanding as it goes from a temperature somewhat higher than room temperature, from a pressure somewhat higher than room pressure to room pressure. So we expand adiabatically, and all we got to do is release the pressure. Again, you can think of catching the expelled air in some sort of a bag or something, a balloon. Okay, so PV to the gamma is, for this case, PV to the 1.4, because we have air being predominantly diatomic. It acts almost exactly as a diatomic ideal gas at room pressure, at room temperature and typical atmospheric pressures or near atmospheric pressures. Okay, so we got PV to the 1.4. Now, what we've got to find P. Okay, P is going to equal some constant over V to the gamma, since PV to the gamma is constant. In other words, okay, PV to the gamma is constant, so P equals that constant divided by V to the gamma. And if we want to get the work done in expanding, which is the purpose here, and I'm not sure I mentioned that, if we want to get the work in the expansion, we're going to have to integrate this expression, the constant over V to the gamma. What is the constant? Well, the constant is any value of PV to the gamma in this process. Particularly, we got the pressure and the volume here. We can do PV to the gamma for our initial pressure and volume. Since PV to the gamma remains constant, then P is going to equal whatever that is, that constant divided by V to the gamma, and our constant is just going to be 0.6 liters to the 1.4, that's our volume to the 1.4, times our 133 kilopascal pressure. That equals, I'm going to go to standard units here, simply because we got this weird 1.4 power, and what effect does that have? Well, we've got to raise the pressure, rather the volume, to the 1.4 power, and we're going to compare that with the pressure, and we want to have the same basic units. We don't want to have liters here and kilopascals over here. You can try to work it out with liters and kilopascals. It's possible. The units of the situation are a lot easier, though, if we keep things as compatible as possible. So I'm writing this now in cubic meters, this in newtons per square meter. This is going to be raised to the 1.4. Among other things, that's going to give you a meter cubed to the 1.4 power, which is a meter to the 4.2 power. Dividing by a meter squared, then the unit of this product is going to have a meter to the 2.2 multiplied by Newton. So the units are going to be newtons times meters to the 2.2 when we calculate this out. And it's going to be kind of important to have that, at least in some applications. Well, okay, so now we're going to do our integral of P dV. The pressure, as we say, is just our constant over V to the gamma. Our constant is just the number that we wrote down here, or the quantity that we wrote down here. Our V is raised to the gamma, the 1.4 power. Now, I've got already the limits on the integral, but we don't know what the second volume is. It's not 0.8 liters as it was before. Okay, so our initial volume, of course, is 0.6 liters. What's our final volume? Well, let P2 and V2 be our final pressure and volume. We know our final pressure to be 100,000 pascals. We don't know our final volume. We want to find the final volume, so we can use that as the upper limit on our integral. Okay, so we know that P2 V2 to the gamma is equal to P1 which is our 133,000 kilopascal, 133,000 pascals, times our volume, 6/10,000ths of a cubic meter raised to the 1.4. Second pressure is this, so the second volume is, well, this divided by P2. So here's the expression. We're solving this for V2, so I've taken the 1 over gamma, or 1 over 1.4 in this case, power of both sides to get V2. So V2 is going to be all this raised to the 1 over 1.4. Again, I'm just dividing this expression by P2, the 100,000 pascals, then taking the 1 over gamma power to get this, and that works out. We have here our 4 over 3 ratio, or 133 over 100 to be more precise. The 1 over 1.4 power applies to that ratio, just by laws of exponents, and the 1 over 1.4 power applies to the 0.0006 cubic meters to the 1.4. The 1 over 1.4 power of the 1.4 power is the first power, so we get 0.0006 cubic meters times this ratio. And then I estimated that, and I got 0.007 cubic meters. So now we have 0.6 liters to 0.7 liters. And that 0.7 is not to be taken seriously. Work it out. That's just a very ballpark estimate, and I probably screwed that one up too. But here's our integral. Now that integral is easy to implement, easy to evaluate. All this is just a constant, so you're evaluating dV over V to the 1.4. I'll complete that in a minute. I want to actually check my estimate here before I continue. Very briefly, I've started to write this up, but I'm going to do that in another clip so that somebody who wants to see that integral worked out doesn't have to watch the whole clip to get to the integration.